All right, so vectors, as you heard in the movie clip, vectors are direction or contain. I guess vectors describe would be a better word. Vectors describe direction and magnitude. So all a vector is a ray in the coordinate grid system. It has an initial starting point and it goes to another point called the terminal point. And here's a picture of a vector right here. It has an initial point and it goes to a terminal point. And the notation is ray notation because that's what it is a ray. The reason why we use vectors is because if you have things like area, time, and temperature, those things can be described with just one number. Like the temperature outside today is 62 degrees. That tells you all you need to know about the temperature for today. But things like force and velocity, they need more than just a number cannot tell you what force is. So if I push somebody with a particular amount of force, or I push the gas pedal on my car with a particular amount of velocity, my car, that person is going to move in a particular direction and go a particular distance, correct? And one number cannot tell you all of that. And so the vector manages to do that. Not only does it give you direction, like this might be a northeast direction, but it also gives you length. Magnitude is length. And so when we looked at magnitude here, you might want to put in there, oh, that means length, it's distance. How far did the object go? And so we have, in order to determine our vector, we have to have an initial point and that terminal point. And then don't forget that the magnitude is length. And then we have two special types of vectors, a unit vector and a zero vector. So a unit vector is important because a unit vector has a magnitude or length of 1. What thing have we been learning about for the last 2 months that a unit vector would be important in? The unit circle. What's the radius of the unit circle? 1. So that's why the magnitude, which if we're talking about a ray, which would be an initial side on an angle in the unit circle, that would have a magnitude of 1. That makes sense that we call it a unit vector. And a zero vector just means that it has a length of 0. In other words, its initial point and its terminal point are the same point. It has a distance of 0. It didn't go anywhere. Vectors that start at 0, 0, they're in what's called standard position. Not all vectors are in standard position, but we can make all vectors be in standard position. In other words, I can take any vector and I can convert it so that its initial point is 0, 0. So for instance, let's say that I had, well, let's look at the component form of a vector, because to change a vector into standard position means that we're going to find what's called the component form of that vector. And by the way, looking back up here, I want you to realize something, that this right here is new notation to you. That means magnitude. It looks like two absolute value signs, but when they're doubled up like that, it means magnitude or length. And how do we find the length between two ordered pairs in the coordinate grid? Distance formula. So it won't be shocking for you to learn that the magnitude formula is the distance formula between those 2 points. And so the component form of a vector puts a vector in standard form. So I'm going to take two ordered pairs. I'm going to call one ordered pair P for my initial point, and let's say that it is at -2, +3. And I'm going to choose a terminating point to create my vector, and it's going to be at +3, +4. So if I were to put this in the coordinate grid, so my first vector, my original vector, starts at -2, +3. So here's its initial point. I'm going to call that point P. And it goes to its terminal point 3, 4, which would be approximately here, give or take. So there's Q. So that's a terrible Q. Let me fix my Q. So my vector starts at -2, 3, and it goes to +3, 4. So this vector has direction and it has length. I don't know what the length is, but we could find out using the distance formula. Its direction is, I don't know, a northeast direction. And we'll figure out the exact angle direction later. Now, if I were to take this vector and put it in standard form, in other words, standard position, in other words, I'm going to make it into its component form, look at what we're going to do. We're going to take P and Q, which I just gave you, and we're going to subtract the X values of P and Q and subtract the Y values of P and Q to come up with a vector that looks like this. How is this, which looks like an ordered pair, different from these two individual ordered pairs? What is the big difference that you see in this one versus, let's say, Q? Not just look at the ordered pair itself. This one versus this one. What's big difference? Look very closely. Look at the parentheses. This one actually has parentheses, doesn't it? The notation all of a sudden changes here to these sideways V's. If you see sideways V's, it means it is a vector in standard position, meaning it starts at 0, 0 and goes to whatever this ordered pair is. And that's what we're going to create. And when we do that, it's going to move this vector down here starting at 0, 0, but it's going to go in the same direction and have the same length. So the lines should be parallel to each other. But I'm just taking this and moving it. And mathematically, we can easily do that by using this following formula. So here we go. So to get my vector in standard position, I'm going, and notice that they always take Q. Q has to come first, which is our terminal point. And so over here, this is my Q. So I always have to take my Q minus my P. So my X values are -2 and 3, but I'm going to change, I'm going to make Q red, and I'm going to make my P blue. So I'm going to take 3, which is my terminal point, and subtract my initial X value, which is a -2, comma. Then for my Y's, I'm going to take my QY value, which is 4, and subtract the initial X value, which is, or Y value, which is 3. And so notice I have my sideways V's, and then I need to perform the math. Don't forget to add the opposite. And so my component form, 3 plus 2 is 5, 4 minus 3 is 1. So that means that in standard position, my vector is going to start here at 0, 0, and is going to go to 5, 1. So these vectors, do they appear to be the same length? Do they appear to be going in the same direction? Yes. Do they appear to be parallel? Yes. So all this did right here, all it did was move this vector from here to here so that we could see it starting at 0, 0. Question? For component form. And we like our vectors to be in component form for a lot of mathematical applications. All I'm telling you, why, I'm not getting to the why yet. You're learning how to do it, and then we're going to use component form in various applications. So don't ask why yet. The reason is we're going to have to use it later. Well, when you convert these two ordered pairs into this one ordered pair, this is a vector that starts at 0, 0. That's what I want you to understand. So this was a vector that was here. I want you visually to see that this vector PQ, I changed it into what's called standard position so that it started at 0, 0. It has the same length. It has the same direction. We've just moved it. And now the vector is called 5, 1. It's the same vector. It's just in a different place. It's like when you change houses. Aren't you the same person? Right? You're just in a different house. You're in a different place. And we're going to use these component forms of the vectors for things later. Isn't this a much simpler looking form than using 2 ordered pairs? And it's going to make your math easier later on. I just showed you. I used this formula right here. And I followed this formula right here. So I showed all of my math. Subtract your x values, subtract your y values. Here's your x value subtracted, here's your y value subtracted. We get the new x and the new y. I don't know how else to explain it. What are you confused on? I just pulled those out of my head.
I know it's 5.1, 7.1 over there. No, right now.
Okay, what are you confused about?
Can I ask you after?
Well, if it's going to confuse you for the rest of the lesson, I need to know what it is that you're having an issue with. Okay. All right, so the other thing that we can find is our magnitude, and so we're going to find that down here in example 1. So look at example 1. We're going to use the same formulas above, and all they want you to find in example 1 is the component form, right here. They're not asking for magnitude, although we're going to find magnitude in this problem because I want to show you how to find it.
Is that, just in the little box, is that V, is this supposed to be surrounded by?
Oh yeah, thank you for pointing that out. The notation is wrong on here, so please make sure that you correct that to double vertical lines. All right, so to find the component form, we first have to have an initial ordered pair and a terminal ordered pair. So this is going to be my initial point. So this is P sub 1 and P sub 2. And then my terminal point is Q sub 1 and Q sub 2. And so I'm just following the formula above. Our step 1 is to find component form. So I'm going to take, since I'm going to component form, my parentheses have changed to the sideways V, and I always take the Q value first, so the terminal always comes first. So the terminal X is 8, minus the initial X is 4. Then my terminal Y is 10, minus my initial Y is 6. Does anybody not know where I got those numbers? And then just do the math. What do you get? What do you get? 4, 4. So this is a vector that's gone from 0.46 to 0.810, and we've moved it to go to 0.00 to 0.44. It has the same direction, it has the same length. And so I put on here, those of you watching the video can't see this, but I put on here, the black is the original vector that starts at 0.46 and ends at 0.810. So isn't that a vector that is also going northeast, a northeast direction? It is. And then this vector here in red is the new component form going from 0, 0 to 4, 4. Do they appear parallel? Do they appear to have the same length in the same direction? And so that's all we did. We just moved the vector. Then they didn't ask for this, but we are going to find the magnitude. Pardon? Oh, they did ask for that. I don't know why I missed that. So they did ask for the length. Excellent. We were going to find it anyway. So we're going to find the magnitude, which is length. And if you note, I've got two different formulas up here. I've got this one, which is the distance formula, as we discussed earlier. But then I have this one. This one is used if we have the component form. Notice that we have V sub 1, which is the x value of the component form, and we have V sub 2, which is the y value of the component form. This right here is V sub 1, so if you want to, you could write in here, this is really v sub 1. That's the difference between the x values of the terminal and the initial side. And this is v sub 2, which is the difference between the y values of the terminal and the initial sides. So since we have the component, why not use this v sub 1 here and the v sub 2 there and use a shortened distance formula form? So we're going to find our magnitude, and we're going to call this vector v for lack of a name, is equal to the square root of, and then I'm going to use v sub 1, which is 4, square it, plus v sub 2, which is also 4, and square that. What's 4 squared? So I have 16 plus 16, which is the square root of 32. Now you can break 32 down into all of its primes, which is 2 times 2 times 2 times 2 times 2, 5 2's. Or what's the biggest perfect square that you can pull out of 32? Bigger than 4. So 16, right? So what's the square root of 16? 4. And then the 2's left over. So our answer is 4 rad 2. So we had our component form, there's our component form, and then we had our magnitude. Any issues, problems, or concerns with finding component form and finding magnitude? Because those are basic skills we're going to use in the following. Fairly simple, yes. You should hope that all of your problems are this way. Unfortunately, they're not. All right, so go to the next sheet. And you'll notice that it goes from example 1 to example 3. Huh? Yes, I am recording it. All right, so all we're going to do this time is vector addition and subtraction and scalar multiplication.
Are those parentheses supposed to be?
Yes, we're getting there.
Okay.
Yeah. So, you mean here?
Yeah.
No, those are supposed to be vector v's.
Okay.
So for these ones, they do need to be changed here and here because they've given us vectors in component form. So you might want to fix those. Then we're going to add, subtract, and then use scalar multiplication on vectors. And we use this skill later on, so we're just going to practice it. It should be a very simple skill for you to apply. Just don't make mistakes when you do it. So let's look at example 3. And we're going to take 2 times v. So all I'm going to do is take 2 and multiply it to vector v, which is 5, 4. And you're just going to distribute this 2 as if it's multiplications in front of parentheses. Normally we don't do this, but we will for vectors. And just multiply it in there. And so you get 10, 8. That's it. And then if we're adding vectors together, I'm going to take my 2 vectors, vector v, 5, 4, and u, 7, 6. And I'm just going to add their x's and add their y's. I like to stack them up so that I have one underneath the other. I don't have to think too much. So when I add their x's and add their y's, I get 12 and 10. So if I take one vector and add another vector to it, I get 12, 10. And to give you an example in your textbook on what vector addition actually physically looks like, you can look at that if you'd like. Or not. Your choice. All right, so then if we subtract vectors, remember when we subtract, we should be adding the opposite. So instead I'm going to be adding a negative u. So I'm going to take my v, which is 5, 4, and I'm going to add to that my vector v, but I'm going to change every sign, vector u, and I'm going to change every sign in u to its opposite sign. So I have a negative 7 and a negative 6. If one of them were negative, it would have changed to positive. And then I'm just going to add. So I end up with a negative 2 and a negative 2. Just basic arithmetic, true? All right, then we're going to combine scalar multiplication with addition. So I have 3 times vector v, which is 5, 4. And I'm going to add to that 2 times vector u. And u is 7, 6. So I end up with 15, comma 12 plus 14, comma 12, which leaves me with 29, 24. And then the last one is just the opposite of vector v, which we already talked about with example C anyway, where we take the opposite of a vector. So I'm just going to take a negative and multiply it, in this case, to vector v, which is 5, 4, which gives me negative 5, negative 4. So any issues or concerns with that? So you should find, for the most part, today's part of your assignment should be simple. So I would suggest you do it because it only takes you about 10 minutes. All right, so then we're going to look at what a unit vector is. So remember, I told you that a unit vector has a length of 1. So if I can take any vector and convert it to its component form, which puts it into standard position starting at 0, 0, then the next thing that we like to do to that particular vector is then compress it, make it smaller, or stretch it and make it longer so that it is a unit vector. So I'm either going to take its length, whatever it is, its magnitude, and shorten it or lengthen it to make it equal 1. And we can do that by the following. So this is how we find our unit vector, is one of these two formulas. I personally like the formula here that I just put my green circle around. And again, this has the wrong notation, so if you would please correct that and make that double vertical lines, that would be terrific. And same thing over here, although I really don't use this formula, so whoop-de-doo-dah. I don't like this formula because it's not the form that we like to have anyway. This is going to get you that form quicker, and this is easier anyway. Although this has its uses in certain situations, which we'll talk about later. So we're going to find a unit vector. What form did they give you the vector in? It's in standard form. If they didn't, they would have given you an initial point and a terminal point. And if they gave you an initial point and a terminal point, you'd need to get it into component form first. Because notice that this uses component form. The assumption is that the vector is in component form, and then we're going to divide it by its magnitude. And so step 1, we're going to take the component form, which is in this case negative 2, 5, and we're going to divide it by its magnitude, whatever that might be. So I don't know what the magnitude is, so then what's my next step? Yeah, find the magnitude. So we're going to find the magnitude. Since I have component form, can't I use the shortcut? Can't I let this be v sub 1 and this be v sub 2 and use the shortcut form of the distance formula? I mean, I can't do anything other than that because I don't have an initial point and a terminal point anyway. So I'm going to take my v sub 1, which is negative 2. I'm putting that in parentheses. Why?
Because of the negatives.
I want that negative squared as well. That was a terrible 2. So anything that gets squared underneath that radical should come out to be positive. So then I get the square root of 4 plus 25, which equals the square root of 29. Can that be simplified? No, 29 is prime. If that could be simplified, you would simplify it. But it can't. So now that we know the magnitude, we're going to take that magnitude and we're going to replace that with a magnitude. So we have negative 2, 5. Lucas, it's much easier to stay awake if we're actually taking notes. Divided by this square root of 29. So you're not done because we actually have to calculate that. So we're going to split that apart into, you're going to make bigger v's, sideways v's, and you've got negative 2 over the square root of 29, comma, 5 over the square root of 29. I am perfectly okay with you not rationalizing that denominator, and so will Math Excel. So this is the answer that they're looking for. This is a unit vector. How can I prove it's a unit vector? What do you know about a unit vector? What's 1? The length is 1. So if the length is 1 and this is my vector, it's a vector in component form, can't I find its length? You're probably thinking, who would want to find the length of that? That looks really ugly. It's actually very simple to find. So step 3, they don't ask for this, but we're going to prove. Proof. It's a unit vector. So we're going to find the magnitude of V divided by the magnitude of V. Because that's what we created, right? V over the magnitude of V. And so all we have to do is take our square root of, and then this is my V sub 1, so to speak, and that's my V sub 2 for the new vector, right? And so I'm going to take negative 2 divided by the square root of 29, and I'm going to put that in parentheses and square it, and add to that positive 5 over the square root of 29, and I'm going to square that. And the most wonderful thing occurs when you square these things. What's negative 2 times negative 2? 4. What's the square root of 29 over the square times the square root of 29? Just 29. Plus, what's 5 times 5? 25 over, again, 29. They have the same denominator, so I can combine their numerators. Don't I get 29 over 29? Which is the square root of 1, which is 1. So that's why this is a unit vector. It has a magnitude of 1. So was that so bad to prove? No. So if I ever ask you to prove that it's a unit vector, I expect to see all of that work, Matthew Thomas. I expect to see all of that work when it's a proof. Any questions on that page? Okay, so we're going to move to the last piece, which is linear form. Linear form is pretty simple, but let me just explain where linear form is coming from. So if I have a coordinate grid, the definition of linear form says that we have two vectors. Vector I, which is noted in component form 0 or 1, 0, and vector j in component form of 0, 1. So that means that I is coming from 0, 0, and so I is coming from 0, 0 and going to 1, 0. So this is the direction and magnitude of I. That magnitude is 1. That's an arrow on the end of that line, just in case you're wondering. And then for j, it's also going from 0, 0, but j is going upwards towards 1, 0. So I'm sorry, 0, 1. And so this is j. So isn't I on the x-axis and isn't j on the y-axis? And between the two of them, they create a 90-degree angle. And if I want to change something like this other vector that's in component form into what's called linear form, we multiply the x value times the I vector, and we multiply the y value times the j vector. So I'm essentially taking the 7 and multiplying it to that vector. Doesn't that give me 7, 0? And I'm taking the 2, multiplying it to that vector, which gives me 0, 2. And I'm adding those two vectors together. Won't that give me 7, 2? So if we want to write it into linear form, the easiest way is just to tack on an I to the x value of the vector and tack on a j onto the y value of that vector. And again, why are we doing this? We're going to use them in various calculations later. So These mean exactly the same thing. They're both vectors. One's in what's called component form and one is in linear form. Yes.
Will this ever be used with imaginary numbers as well?
It does closely resemble the complex number ai plus b. And if you think about it in terms of the coordinate grid system, this is the I-axis, and this, which is the imaginary axis, and this would be the real axis. So it has some similarities to it, although
Does
they
I-
aren't related in that way.
Does I ever help in the formula? With,
Not as an imaginary number, no. So, reason would state that why did we use I? Why didn't we use, W or something else? I don't know, I wasn't in
Why
charge.
don't we just use X?
Because I wasn't, X is way too overused, isn't it?
Yeah.
Yeah,
but-
X is used for a lot of things. But I was in charge, so we're going with what the much smarter people than I went with. All right, so let's look at example 5. We're going to write linear combinations of unit vectors. So look at what they gave you. They gave you an initial point and a terminal point. Is this a vector in component form or not? No. So this is not two different vectors. This is an initial point and a terminal point. So if I want to write this vector in linear form, I have to have its component form. So number 1, find component form. So for our purposes, this is p sub 1, this is p sub 2, and this is q sub 1, and this is q sub 2. Our initial point and our terminal point. So we're going to go all the way back to example 1 where we found component form. So we're going to use our sideways v's. And I always take the terminal point first. So my x terminal point is -1. And I'm going to subtract from that the initial x, which is 2. And then for my y, I'm going to take my terminal y, which is 3, and subtract from that my initial y, which is -5. Don't forget to add your opposites. So I get plus a minus here and plus a positive there. And what do we end up with? -3, 8. So now that's a vector in standard position starting at 0, 0, component form. So then if I want to write it in linear form, we just quite simply tack an I onto the x value and a j onto the y value. So we have -3 I plus 8j. Done. That's it. It's that easy. Now, what if the 8 were negative? What would you have written? -8j. So I don't want to see double signs. I don't want to see plus and -8j. And then the last thing that we're going to do today, and you're going to do this on your own, and I will quietly do it up here, and then I'll show you the answers, but you're going to do vector operations. You're going to add, subtract, and use scalar multiplication with these two vectors, v and u, in linear form. Yes?
What's like the one to like the I and J?
Well, you're going to see. We're going to use them later on in various equations. Yeah, as you can see, day 2 is going to be directional angles, and you can see the I and J is showing up there. It just depends on what application we're using the vector in, whether it's written in linear form or component form. Different applications use different forms, and so we have to be comfortable with both. And so you're going to go ahead and perform these operations. So I'll give you about 2 minutes. I'm going to cover it up while you're doing that. Not right now. You just try to do it on your own. Just add, subtract them, Jason.
Do I need to do it like that?
You have to put the I, no, you're just putting I and J. There should be no sideways V's. When you get an answer, share it with those around you. Share, share, share. I don't hear you sharing. Everybody's sharing. Talk. Matthew Thomas, actually do the problems and discuss it.
Yeah, I did.
Okay, discuss it with somebody. Who'd you discuss it with? Nobody. Talk. All right, here's your answers. Do we agree or disagree? Notice that when we did problem D, instead of subtracting, I multiplied vector v by a -3 and just added. It's much easier to use addition rather than subtraction. And please note that they swapped around the u and the v, so don't get comfortable in these problems that some of you might have put the v here inadvertently and the u here, and that's why you got the wrong answer. Any other issues, problems, or concerns with what we did today? Okay. Nothing? Good. All right, so today we're going to actually apply what we were doing yesterday by finding the direction or the angle of your vector. So as we look at this example right here, this is vector u. Vector u is in the unit circle. And so vector u is a unit vector because its radius would be 1. True? So we have here, if u is a unit vector such that theta is the angle measured counterclockwise, because we always go from the initial side up to the terminal side. So that vector is your terminal side in that unit circle. And so theta is that angle that is created. We get the following values. Notice that we have the side opposite and the side adjacent. The side opposite is the y value right here in that ordered pair. This is the ordered pair at the very terminal point. This is a vector that's in standard position, so it starts at 0, 0. It ends at whatever that value is, x, y. And if the vector is in component form, that ordered pair that it ends at is your x and your y. So your opposite value, you would know that side, and your adjacent side, which is x, you would know that side. Also, don't forget that the x value of any ordered pair is cosine and the y value is sine in that unit circle. If I were to convert this component form with sine and cosine, because that's what we use to find angle measures, all we have to do to go to linear form is tack an I onto the x value and a j onto the y value. That's it. So this becomes important for you to know. We're going to use those forms a lot, where this is your component form, and then this is your linear form. Well then, what if we don't have a unit vector as our vector? What if its magnitude is not 1? How are we going to find the component form and the linear form? So we end up looking at these right here. And I'm going to point out to you also that your textbook changes the notation for magnitude to just single, what they look like, single absolute value signs. I really don't prefer that, because then you guys think they're absolute value signs. And so you might see that on Math Excel. So please note that I still prefer these written as double signs, although you're going to see in your textbook and probably in Math Excel that they're just single. It's just a difference in notation from publishers. but I prefer the double to differentiate it between absolute value. So if I have a vector that is not a unit vector, we are going to have to take the magnitude of that vector as a scale factor or a scalar multiplication into that vector itself. So if I wanted to find the actual x value, I'd have to multiply it to the magnitude, the sign value multiply it to the magnitude, and that becomes the actual component form of that vector. Typically, you'll see me using this form, although it looks more complicated, more often to find the component form because it tends to be easier. So again, you're taking the magnitude times the cosine, which is your x value, tack on an I, plus the magnitude, so that should be double, times the sine, and then tack on a j. The last thing I want to remind you about is tangent. Isn't tangent of this angle right here side opposite over side adjacent? So tangent is either sine over cosine or y over x. And why am I using an inverse tangent here to find theta? Because if we're finding theta, don't we use the inverse tangent? If we're finding the angle, theta is your angle, we always use the inverse trig function. So we like to use tangent because I tend to have this ordered pair here, which means I have the side opposite and the side adjacent. The magnitude is your hypotenuse in any of these right triangles. So sometimes you'll have that magnitude, sometimes you have to calculate it. So we tend to use tangent because we don't have to calculate these x and y values. Just a reminder that if you're given something in linear form, the coefficient of the I is your y value, or is your x value, and so it's going to go in the denominator, and the coefficient of your j is your y value, and so it goes in the numerator. I don't tend to use these because I'll always convert it to component form. All right, so based upon that information, Owen, you might want to write here component form, and then this is linear form. All right, so look at your final slide, final page, and we're going to do examples 7 and 8 today. So example 7 says find the direction angle of each vector. It does not mention magnitude, but we could find magnitude if we had to, and in Math Excel will ask you to do both. For here, I have a vector that is in standard position. I know it's in standard position because they've given it to me in component form. So it starts at 0, 0, and it goes to that point of 3, 3. So we're going to make a coordinate grid. And so my vector goes to this point, which is 3, 3. So it goes from 0, 0 to that 3, 3. And so what they want you to find is theta right here, from here to here. That's an arrow. It looks like a flower. That's an arrow. So in order to do that, I'm going to drop down and make a special right triangle straight down to the x-axis. So I actually know parts of this triangle. I don't know the hypotenuse, which would be our magnitude, but I do know the side opposite. What's the side opposite? 3, because that's the y value in the component form. And what's the side adjacent? Also 3, because that's the x value in that component form. Please name for me the type of triangle that this is. Name it with proper side names. No, proper side names, like scalene, isosceles, equilateral. So it's an isosceles right triangle. So write yourself a note, all right triangles. I turned it off for a minute. All isosceles right triangles are 45, 45, 90 triangles. So a lot of you already recognize that, but just bear that in mind. It doesn't matter if the sides are 5, 5, -7, -7. If those legs of that right triangle are equal, it's an isosceles right triangle. It's a 45, 45 triangle. So I know that theta is equal to 45 degrees. And so that's really the answer to the question, but let's assume that we didn't know that. Let's use tangent. So mostly because I know the side opposite and the side adjacent, and that would be tangent. So tangent of theta is equal to y over x. Tangent of theta is equal to, our side opposite is 3, our side adjacent is 3, which means that tangent of theta is 1. And then you could just use your knowledge of special right triangles, knowing that tangent is 1. Some of you have learned those. Or if you didn't know, you could throw into your calculator the inverse tangent of 1 is equal to that 45 degrees. And so this is the answer that they're looking for. And we found it 2 different ways. So that's using prior knowledge. But look at part B. Part B is in linear form. So if I were to put that into component form, what would I have? What's its component form? 3, -4. Good. So that means that its y is -4, its x is 3. And so if I put it into the coordinate grid system, bless you. So -3 or +3, -4 is right here. So that means that my vector coming from standard position going to that terminal point would look like, whoops, I missed just a little. It's close enough for government work. But when I make my right triangle to the x-axis, our theta is not what you think it is. Our theta goes from here all the way to here. It always goes from the initial side of the unit circle counterclockwise till you hit that vector. And so this is our theta here. So that means that this right here is theta prime. Do you remember our use of theta prime earlier? That's our reference angle. And so we have to use our reference angle and the knowledge that this is 360 degrees here. So a couple of interesting things occur. Let's first label our triangle. So what is side opposite theta prime? -4. What's side adjacent? +3. So again, I'm going to use tangent. I don't know my magnitude. Move this over a little. So my tangent of theta prime is equal to side opposite, which is -4, over side adjacent. So to find theta prime, what am I going to use? This is not a special right triangle. It's not a ratio that we recognize. So how am I going to find theta prime? Huh? I'm going to use my calculator. How do I punch it into my calculator?
Are you gonna do the sine thing?
No sine. Inverse tangent. So remember, if we're trying to find an angle and we're using the trig function tangent, if I'm going to find the angle in my calculator, we want to find the inverse tangent of the ratio that it's equal to. So in this case, that's what you're going to plug into your calculator. What do you want to make sure your calculator is in? What mode? So make sure you check your mode first, because it might have somehow crazily switched. You're like, I didn't do that. Yeah, you might have pushed a button inadvertently. So always check that mode. Make sure it's in degrees because we want degrees to come out of the calculator. And so if I do inverse tangent of -4 divided by 3, I get a negative answer. So, whoops, I don't want green. So theta prime is approximately equal to -53 degrees, 0.13. I'm going to go out to 2 decimal places. So let's talk about that. This is a negative degree according to the calculator. Does the calculator know that my theta prime is in quadrant 4? No. But it supposes that it's in quadrant 4 because it knows that it's a negative value. So tangent is negative in 2 quadrants, isn't it? Either this quadrant or this quadrant. So both of those quadrants, I would have come out with a -53.3 because tangent is negative in quadrant 4. But I really don't need this to be a negative angle. I want to really view it as its absolute value form. So whenever you use your reference angle, view it as its positive answer because this is a reference angle. So use the positive value of the reference angle. You should be writing this down. If I'm writing it down, you should be writing it down. And so really theta prime is positive 53.13. So how am I going to find theta? So theta is approximately equal to what? Not 180 because it's not close to 180. 360. So it's 360 minus this reference angle, which is 53.13 degrees. And that's an approximation, so this is an approximation. And so I end up with 306.87 degrees. That's my directional angle in quadrant 4. So B was a slightly more difficult problem, but you have to use your logic reasoning and your knowledge to help you get there. Okay, so questions on those two? Makes sense. Use prior knowledge along with our vector knowledge. Now, if they asked you to find magnitude on top of that, then you would just use your formula from page 1 for your magnitude. This last part, last question is find the component form and the linear form. So we need both the component form and both the linear form. I choose to find the linear form first. I find it easier. You might think that the formula seems a little bit more complicated, but it's easier to go from linear form to component than vice versa. So we're going to find our vector by taking the magnitude of the vector, and this is, I'm getting this formula from the previous page, times the cosine of the angle, and then tack on an I, plus the magnitude of the vector times the sine of the angle, and tack on a j. So it's handy to know what quadrant our angle is in. So I'm going to sketch my angle. Where is 210 degrees? Quadrant 3. So I'm going to put my vector in standard form into quadrant 3. So we're really finding this as our theta. But we're going to draw a reference angle or a reference triangle to the x-axis. And so really this is our theta prime here. There's a couple things I know. I know that theta is 210 degrees. So what is theta prime? What's our reference angle? Yeah, what's 210 minus 180? 30 degrees. So I know that I'm dealing with a 30, 60, 90 triangle. I also know that my magnitude is 100. So that means that that's the length of this vector. The length of my vector, that hypotenuse of the triangle, is 100. However, I really don't use that to help me find my sine and my cosine, because I need the cosine of theta and the sine of theta. Not theta prime, but theta. If I find the sine and cosine of theta prime, won't that give me the sine and cosine of 210 degrees because they're coterminal? Right? So we are going to do that. I need to fill out my triangle. So what's side opposite theta prime? If it's 30 degrees. What's side opposite 30 degrees? 1. But in this case, isn't it negative 1? Because it's the y value is negative in quadrant 3. And what's side adjacent? Negative radical 3. And what's the hypotenuse? 2. I know the hypotenuse currently says 100, but for our purposes, for finding sine and cosine of theta prime, we're using the special right triangle. So we're going to use 2 as our hypotenuse. And so what is the sine of 30 degrees in quadrant 3? Negative 1/2. And what is your cosine of 30 degrees in quadrant 3? Negative radical 3/2. Both ratios are going to be negative in quadrant 3 because only tangent is positive. So then we're just going to fill out the above formula with the things that we know. So I'm going to put in my magnitude, my cosine, tack on an I, put in my magnitude again, my sine, and tack on a j. Well, my magnitude is 100. That's 100. And then my cosine, we just determined, was negative radical 3 divided by 2, and our sine was negative 1 divided by 2. So all that's left is really to do the math. And you have to pay attention in Math Excel to whether they want an exact answer or a decimal equivalency. In this case, if it's a special right triangle, my assumption would be it's an exact answer. So as I multiply 100 to the negative rad 3/2, the 2 cancels into the 100 50 times, and I get negative rad 3 times 50, which is negative 50, radical 3, and then times the I. Make sure the I clearly is not underneath that radical 3. And then when I simplify the 100 times negative 1/2, the 2 goes into 2 once and into 150 times, and 50 times negative 1 makes it a negative 50, and then tack on the j. So you should have a minus, not a plus minus. And so this right here, this right here is our linear form. And it's very easy to go from there to our component form. So our component form has those sideways v's. So what's in my component form? Yeah, just take the coefficients of I and j and let them be x and y. So we have negative 50, radical 3, comma, negative 50. And so that becomes my component form. Done. Any issues, problems, or concerns with that?